Hello and welcome, ladies and gentlemen, to the last lecture set video in this course. We'll have some R videos after this, but this is the last lecture set video that we're going to have. In this video, we're going to be talking about a couple of catch corners on multiple linear regression. We'll be talking about things like assumptions. We'll be talking about a couple other things too. Getting in an APA write-up. I can't remember what else, so we'll get to explore together. But yeah, let's go on and get started with our last lecture set video. All right, so for our assumptions, it's worth mentioning all of our assumption checks, because we designed our assumption checks based on graphical methods using kind of general terms. All of our assumption checks are identical to simple linear regression. So all of that stuff is still the same. Now, with that said, because we're introducing multiple variables in multiple linear regression, we now have more than one independent variable. We have a couple more. So I mentioned earlier when we talked about interactions that interactions, if we don't include them, are now a new statistical assumption. So if I don't include an interaction in the model, it's assumed that there is no interaction term. And that may or may not be a good assumption. How do I check that assumption? Well, I include the interaction term and I see, is it significant or not? So by including the interaction term, you can check if there's a significant interaction. But if you choose not to include it, realize you are assuming that there is no interaction. That's an additional statistical assumption that you're making. All right. Another one that we have here is collinearity and multicollinearity. Collinearity and multicollinearity refer to the fact that we make an assumption with multiple independent variables that the independent variables don't overlap too much, that they're not too correlated with one another. When this is violated, there's some unpredictable effects on things like parameter estimates, that is the effects of the variable 1 on the outcome and variable 2 on the outcome. Both of those betas can do weird things. Also on the tests. But it's worth mentioning this doesn't impact prediction. So if you're really looking just for prediction, you don't really have to care about this. But if you're looking to explain effects, I want to explain the relationship between the independent variables and the dependent variable, or I want to interpret the tests. If you're looking at prediction, you don't really care about the tests. But if you want to interpret the tests, then you want to be careful that you don't really have this collinearity, multicollinearity, or an issue with that going on. Now, it is worth mentioning, even if you want to do prediction, that if you have really extreme violations, that is, one variable is perfectly the same as the other variable or a linear combination of other variables, your model's just not going to run. So be aware of that. So for multicollinearity, you have to remember, we don't always just have two independent variables in there. Sometimes we have 5 or 10 independent variables. And when we talk about multicollinearity, I'm not just talking about the relationship between one independent variable and the other. I'm talking about kind of the joint relationship between one independent variable and all of the other ones. So to check multicollinearity, essentially what I do is I see how much, if I have, in my example, in my hands here, 10, let's say I'm looking at this variable here, I want to see how much variability in that variable is explained by all of the others. So how we do that is literally we make regression models. I make a regression model with this one as the outcome, and I look at how much variance is explained. I do a regression model, I calculate an R squared, and that's how much variance in this one is explained by all the rest. Now with two variables, I can just do correlations, right? So I just look at the correlation between the two independent variables and I can see how correlated are they. With multiple independent variables, again, I do that regression approach, and actually I summarize that in a statistic called the variance inflation factor, or VIF. Now, there's another one called tolerance, which is just 1 divided by the variance inflation factor, and they have inverse interpretations. We won't talk about it. We'll just talk about the VIF. So for each variable, and this is important, for each of my independent variables, I'm going to have a VIF. So for the one I was talking about earlier, I'm going to have a VIF. What I do is I run a regression of all 9 other independent variables, and I treat the one I'm interested in as the outcome variable. And I find the R squared and I write it down. And to calculate the VIF, I do 1 divided by 1 minus the R squared from that model. And that's the VIF for that first variable. And then I go to the second variable. I look at all of the other independent variables, this variable regressed on all the other independent variables. This one's the outcome, the dependent variable. All these are the other independent variables. I find the R squared, and then I do 1 over 1 minus that R squared, and that gives me the VIF for this. And if that sounds like it takes forever, if we did it that way, it does. The computer does it almost instantaneously, so we're not going to worry about doing all that. But that's where this comes from. And again, if you think about R squared, that's the amount of variance being explained in each of these independent variables by the combination of all of the other ones. And so why I talk about this in such detail is to give you the picture that I'm not just looking at one variable versus another. I'm looking at one variable versus all of the other independent variables. If there's only one other independent variable, that's fine. We can just do the correlation between those. But the complexity of multicollinearity comes from the fact that sometimes you have many other independent variables. VIF greater than 5 or greater than 10, according to some, is kind of like a rule of thumb of when you have a problem that's too high. I've heard it, there's just a bunch of different numbers. I'm not even going to say all the different ones I've heard. I've heard a bunch of different numbers for this. So just realize there's a bunch of different numbers for this. Now to solve, let's say I have a really, really high collinearity. What I can do if I have that case is I can do a whole bunch of pairwise correlations among all my independent variables to see, is it the case that 2 of these are just lining up really closely? And if there is the case that 2 independent variables, like why is this one so heavily explained? Well, it's because 1 of the other 10 is highly related to this. What I might do is I might just combine these 2, take an average if I can, if that makes sense, or maybe I'll just drop one of them out of the model. Remember, what a high multicollinearity says is these 2 variables are very, very, very similar to each other. So dropping one of them out of the model is not as crazy as it sounds. It's essentially saying they're telling the same story. Why do you have 2 of that in there? And so if I drop one out, I would just use the one that I keep in. Another way is to combine variables. I said take the average. That's usually not what we do. Well, I guess that's not untrue. There's a couple of different ways to combine variables. You can use fancy method like principal components. Yeah, you can use fancy methods or you can use simple methods, but typically we drop or combine. This was our other topic, standardized regression coefficients. Yes. All right. Oh, and I'm glad we have this here. All right. So as you may have noticed, the regression coefficients don't change with the scale. So let me say, remember when we talked about correlation, this is a while ago, but when we talked about correlation, we said that the correlation was scale invariant. So whether you measured someone's height in terms of millimeters or miles, it doesn't matter. Those numbers are going to be very, very, very different than each other, but the correlations are going to be identical. It's kind of a cool thing in correlations. And the test of correlations is going to be the same, and the confidence interval for correlation is going to be the same no matter what the scale is. With regression, while the test is scale invariant, the size of the coefficient does change when the scale of the independent variable is changed. So if my independent variable is in miles, my coefficients get really, really, really small, and my independent variable is in millimeters, my coefficients get really, really, really big, even if the test is the same. Now, if the scale isn't of particular importance, this can be a problem because sometimes my parameter estimates can look really big or really small, even if they aren't. And that's just because of the scale the variable's on. So if the scale's on if the variable's on a meaningful scale, then I want to keep that because it means something. You know, a single unit increase is actually meaningful. But if the variable isn't on a meaningful scale, then I may not worry about keeping it. And the fact that that decision has to play a role here is a bit problematic. That's of a bit of concern. So there's a couple of ways you can approach this, one of which is to standardize all the independent variables and the dependent variable before the regression. That is, for each variable, subtract the mean and divide by the standard deviation. Note that this doesn't change the way in which the variables are distributed, but this does change what the values represent. Now the values represent, or on the scale of, the mean is 0 and the variable has a standard deviation of 1. So the numbers represent how many standard deviations away from the mean they are. Again, this doesn't change the distribution at all. So there's a lot that this doesn't really impact, and this is a legitimate approach. What this does change, though, is the meaning of the numbers. More specifically, it changes when I say a single unit increase, what that means. With an x value or any other independent variable value, when I talk about a single unit increase is on the scale of that independent variable. But if I standardize the independent variable, a single unit increase now represents an increase of a standard deviation. And if I have multiple different independent variables on different scales and standardize them all, now a single unit increase means the same thing for each one. For each one, now it means an increase of 1 standard deviation. What this means in terms of regression is when I run this, now all of the parameter estimates are the expected change in the standard deviations of y for every standard deviation in x, after accounting for the other variables, because this is multiple regression. So in this case, the betas, the parameter estimates do change, and it's because the interpretation has now changed. Whether or not you standardize the dependent variable is a thing that we could talk about and debate. I don't know that that's particularly as important, but standardizing all the independent variables, again, let a single unit change represent a 1 standard deviation increase. Now, I'll say we only tend to do this for continuous independent variables. This doesn't really make sense for categorical independent variables. But if we do this for all of our continuous independent variables, it lets us compare the coefficients to one another. Is that a good thing? It depends on the context, but that's the goal. And people who really like this really think it's a good thing. All right, here's the problem, though. Well, not really a problem. It's an irritating thing to me. And I don't know if you'll ever use this. I don't think this is on your homework, so you don't need to worry about it in your test, but interesting to know perhaps. The sample estimates for these, remember all of our sample estimates for our regression coefficients were B. Well, the sample estimates for this type of thing is beta. So these are sometimes called beta coefficients. But this is super confusing because our population values for our regular regression coefficients are also beta. And yeah, that is super confusing, and I hate it. I think it's terrible. I really, really, really don't like it. It's so confusing. It's confusing when reading reports when people try to do this. It's confusing when reading reports when people don't try to do this. And they try to talk about beta, and you wonder, are you talking about these beta coefficients from standardized regression, or are you talking about the population coefficients? I don't know. Beta is again, I hate it. I hate it a lot. Anyway, these coefficients are sometimes useful. I professionally rarely use them, but occasionally someone will ask for a comparison, and this is the best or a good way to go about it. Maybe not the best way, but this is a good way to go about it, is by standardizing the coefficients so that we can compare the impact on the outcome between 2 different independent variables on 2 different scales, and standardize that a little bit. Again, the new interpretation is for standard deviation increase in the independent variable, what's the expected change in the outcome variable? And if we standardize the outcome variable too, it's for a standard deviation increase in the independent variable, how many standard deviations does the outcome variable change? And again, for 2 independent variables on 2 scales, it's nice to look at standard deviation increases because that makes them more comparable than they originally were. All right, well, let's put it all together. Let's try an APA write-up for a multiple regression. Multiple regression was conducted to predict job satisfaction. So you can see we're talking about the multiple regression. We're talking about what we're trying to do. We're trying to predict Job satisfaction is our dependent variable, and what we're trying to do this. Workload and perceived organizational support are our independent variables. We talk about how we assess our assumptions. Assumptions were evaluated using residual plots and QQ plots. Those are from simple linear regression, and those are used in exactly the same way as we did in simple linear regression. And I mean exactly. In fact, all the equations and calculations, all the R code that we talked about, all of those are exactly the same. And an examination of VIF, the variance inflation factor, none of which indicated concerns. That's lucky for us. Note that if one of them indicated concerns, I'm not going to write none indicated concerns. I'm going to talk about the concern. I'm going to figure out in the simple linear regression, we talked about how our assumptions relate to our conclusions and like in what way those interplay with one another, in what way the violations interplay with the conclusions, like do I have to care? So I would talk about it and I would fix it if I had to. For the new one, the VIF, the fix is essentially drop one of the variables that's misbehaving. The overall regression model was significant, so I have my 2 and 97 degrees of freedom. Again, this is an overall test. That 2 is the number of parameters, number of independent variables, 2, and then the 97 is the degrees of freedom error, n minus p minus 1. The 15.32 is that test statistic, and I have my p-value. And I'm not saying p equals 0. Remember, p never equals 0. If p is rounded to 0, instead I write p is smaller than the smallest number I can do with that rounding scale. So if I'm rounding to 2 decimal places, the smallest number I can do is 0.01, and if p is rounding to 0, instead I write p is less than the smallest number that I can do on that rounding scale, 0.01. And it explained approximately 24% of the variance. Where am I pulling that from? Well, in this case, I'm using the R squared adjusted for the fact that as I add new independent variables, that variance increases a little bit with regular R, but it doesn't necessarily do that with R squared adjusted. My perceived organizational support was significant predictor of job satisfaction, and I provide my parameter estimate, my test statistic value, and my p-value. Indicating higher support was associated with greater job satisfaction. Fantastic. Workload was not significantly related. And notice that these relationships are after accounting for the other variables. So I'm looking at workload on job satisfaction, and the interpretation is workload is not significantly related to job satisfaction after accounting for the other independent variable. And I have that, and then I state a little thing, these suggest blah, blah, blah. And I note that this is context dependent. So that's our APA write-up for what a multiple regression could look like if I were reporting out these results in a professional report to a colleague, to a boss, to a client, or, you know, from another hat, this is what results might look like. You might see these results if somebody ran an analysis and submitted these to you. And that's what these numbers mean and where they come from if you ever see something like this being given to you. Ooh, all right, ladies and gentlemen, we are closing out, beginning the next stage, anything you want. Absolutely. I don't know. I'm nostalgic. I enjoy this class. We have done a ton in the course. We've done so much. So thank you so much for sticking with me. But let's close by taking a moment and kind of synthesizing everything that we talked about into kind of one big picture workflow thing. The first thing we have to do is we have to figure out our situation and select the appropriate analytical model. That's our first analytical step, is selecting the appropriate thing. Remember, t-test, ANOVA, regression, correlation, all the same thing. But remember that table that I put up at the beginning of our simple linear regression slides that talked about, well, my independent variables are continuous or categorical, my dependent variables are continuous or categorical. This is what I have to do. That's the kind of thing that I want you to consider when you're selecting the appropriate model. Remember this regression approach, or more generally stated, the GLM, General Linear Model. This is a fantastic and extraordinarily flexible approach. So if your outcome is a continuous variable, this is the world you're going to be in. Next, you'll check your assumptions. And remember, if it's slightly broken, don't worry about it. But if it's badly broken, it really does need to be fixed. If your assumptions are broken, all of the logical arguments you're making based on the calculations you're doing, all of that is flawed. And, as much as we like being right, we kind of like to be right every once in a while. So it's not just about winning an argument. It's not just about providing data that support your perspective. It's about getting as good of an insight in the situation as you can. And when those assumptions are broken, again, those assumptions underlie all of the logical components of our analytic approaches. So if those assumptions are broken, all of the logic associated with our analytic approach and conclusions, all of that is flawed now. So check them, and if they're okay, then move on. Remember, the default assumption is that they're okay, so you're looking for red flags. Also remember, we talked about assumptions in the context of simple linear regression and multiple linear regression, but remember, t-test and ANOVA are all under the same banner, and t-tests and ANOVAs all have those same statistical assumptions. So all of this stuff really has the same assumptions. While we didn't talk about testing it in a t-test and ANOVA, you should, and you should test it at this stage. If you're doing interactions in the model after a test of assumptions, this is when you test your interactions. If they're significant, you don't go on to that main effect. But if they're not, then you can go on to those main effects, and you can interpret them. Now, we talked about two different models that can handle multiple independent variables and thus handle interactions. One was the two-way or multi-way ANOVA, the factorial ANOVA. And in that case, if you don't have an interaction term, you can go on and interpret those main effects and not really worry about it. But if you're doing multiple linear regression, remember, if you have an interaction effect and it's not significant, you have to be careful when interpreting the main effects of the multiple linear regression, because now those are still interpreted at 0 for the other independent variable. So you got to be careful about that and potentially do an edit to center those independent variables to make them more interpretable. Of course, if you do have a significant interaction, check out one of those interaction plots. Again, what that says is the impact of, say, weight on horsepower, the impact of your independent variable and the dependent variable depends on the different levels of the other independent variable. With good assumptions and no interactions, then we can look at the significance of main effects. So remember, I look at statistical significance before I interpret them. If they're significant, then I look at the confidence intervals, and I look at the low end and the high end of the confidence interval and interpret those in terms of the context, because these are the top and bottom of the reasonable range provided by data. Again, for the confidence intervals, if it's significant, they're going to tell in some way the same story, but they might still be far apart, and they might tell drastically different stories. They're not going to go in the opposite direction with a significant effect, but they might still bear different interpretations. If so, then I would provide a different interpretation for each and acknowledge both of those contexts are reasonable, and we should take those into account when we make a decision. Otherwise, I'd just interpret the estimate. If the significance of the main effect is not statistically significant, then I wouldn't interpret the estimate. Remember, my default is that this is now 0. There's no effect. And it's not because there's evidence that there's no effect. It's because that's my default, and there's not enough evidence to convince me that there is an effect. With that said, I might provide a confidence interval to show a reasonable range of where the effects may fall based on the data. So, that's my closing thought. That's kind of how I would approach analysis based on everything that we've done in this course. That's kind of a generic workflow to consider. And I hope you take it with you, and I hope it's helpful as you look at stuff. But man, with that, ladies and gentlemen, you have finally reached the end. So, ladies and gentlemen, thank you so much for sticking with me through this course. It has been my pleasure to get to work with you this semester, or this whatever timeline we're working on in this course. It's been my pleasure to get to work with you throughout the duration of this course. So thanks for sticking with me. Thanks for sticking with me through this video, through this lecture set, and through this course. It's been a good ride. Now, I say the end, but remember, there's a few R videos on how to implement multiple linear regression, or software videos on how to implement multiple linear regression coming up. So don't forget to check out those. But again, thank you so much. I hope you enjoyed this video, and I'll look forward to seeing you in the next one.